Welcome back as we continue to pursue better ways of finding digits of pi. Last time we numerically integrated a quarter circle. These are the results of that. Even after dividing the area into 128 panels, neither Simpson's rule nor Romberg integration gave us more than 3 digits past the decimal point. Today, we are going to refine our method to get better performance. Just a quick reminder from last time. We divided a unit circle into 4 equal pieces and then integrated. Here is an illustration of the quarter circle divided into 4 panels. Notice the green section. That represents a significant portion of the area that is not captured by our panels, which ultimately reduces our digits of accuracy. Even if we increase the number of panels, the undefined slope at x equals 1 will give us the same trouble. How do you think we could overcome this problem? Well, we could divide the unit circle into 12 equal slices instead of 4. Now the slope at the rightmost edge is no longer undefined. Even with 2 panels, we have far less area that is unaccounted for. Our numerical methods are going to give us the total area, as represented in pink. The pi over 12 slice I have labeled A1. In order to get that, we have to subtract the area of the triangle beneath it, which I have labeled A2. In case you were wondering how I got square root of 3 over 8, this is how. The area of a triangle is 1/2 the base times the height. As I was just saying, we have to subtract A2 from the total area to get A1. Substitute those values. Then to get pi, multiply both sides by 12. Very good. So what is A total? A total is the numerical approximation of area. This can be obtained by using Simpson's rule or the trapezoid rule, which will lead into Romberg integration. Feel free to revisit those lessons if you'd like a refresher. Otherwise, I'm going to continue with applying these methods to calculate pi. Here I have shown function evaluations for 1, 2, 4, and 8 panels. The same pattern is used for higher numbers of panels. These are the numbers we plug into Simpson's rule. Notice I've started with 15 digits after the decimal. That means my final answer can be no more accurate than 15 digits. Here is a summary of that. It looks like each time we double the number of panels, our accuracy increases. By 128 panels, we have 10 digits of accuracy, as underlined in red. Error is the difference between the exact value of pi and our approximation using Simpson's rule. Once again, we see the base 10 logarithm of error. What's going on with this? Well, within rounding, this is basically counting the number of zeros. I have underlined 10 zeros in the last row, but the same pattern applies to every other row. If you need to convince yourself, pause the video, count the zeros for each error, and compare that to the number in the last column. Here is the result of Romberg integration. As with Simpson's rule, we see more accurate results as we increase the number of panels, which makes sense. Notice the most accurate value for a given number of panels is the rightmost entry in each row. Here I have taken the base 10 logarithm of each error. This approximates the number of digits of accuracy. For illustration, I have highlighted a particular entry with blue. There are 5 zeros in the error, which is what 5.5 rounds down to. The same pattern applies to every other entry. Pause the video and verify a few for yourself. Consistent with what we just saw, the most digits of accuracy for a given number of panels occur in the rightmost entry of each row. So what's going on with the boxes highlighted in green? Basically, we have reached the limits of this software. It can store no more than about 15 digits. The error terms are so close to 0 that the computer reads it as exactly 0 rather than a very small number close to 0. If you remember your algebra class, the logarithm of 0 is undefined, so we get an error message. Here I've summarized the 2 methods so we can compare side by side. Which one seems to perform better? A plot shows clearly that Romberg integration outperforms Simpson's rule. Because we reached the limits of the software at 128 panels, we can do a bit of extrapolation. It looks like we could have gotten 16 or 17 digits of accuracy. Of course, we are limited to about 14 after the decimal with this software, so that's where we must stop for now. This is the same data plotted with a logarithmic scale on the x-axis. This allows us to extrapolate using a straight line. Again, it looks like we could have obtained 16 or 17 digits of accuracy using Romberg integration and 128 panels. Another table for side-by-side comparison. We've maxed out at 14 digits past the decimal with Romberg integration. Meanwhile, Simpson's rule gave us 10 digits. At any rate, dividing the unit circle into 12 slices gave us much better results than the quarter circle. Enough with circles for now. Can you think of any other functions we could numerically integrate to calculate pi? Mull that over for a while, and stay tuned for another lesson in which we will explore answers to that very question.